I'm here with UC Davis Associate Professor Alyssa Kendall and ASU Assistant Professor Mikhail Chester for our webinar today on Lifecycle Assessment and Transportation Project Planning. So today we'll be hearing from the two professors, getting an introduction to what lifecycle assessment is, how it can be applied in the context of transportation planning, both kind of in an academic context, but also in a practical context, and how it might integrate with existing planning and environmental review processes. So without further ado, I would like to hand the presentation over to Alyssa Kendall, who's Associate Professor in the Department of Civil Environmental Engineering at UC Davis, as well as Chair of the Graduate Energy Group. Alyssa?
Thanks for the introduction, Juan. It's a pleasure to participate in this webinar with Professor Chester. So I'm going to start out by talking a little bit about what life cycle analysis is and how we go about doing it. So life cycle analysis, or LCA, emerges from the field of industrial ecology. And the core idea around industrial ecology is that we look at the natural ecologies and try to mimic our engineered or human-mediated world to perform like a natural ecology. A natural ecology exhibits cyclic flows of energy and materials, and if we're able to do that, then we can design more sustainable systems. So life cycle analysis, or LCA, emerges from this field. And it's basically a tool that emerges from the field, and it's a method for characterizing and quantifying environmental flows for a product or service from cradle to grave. And so we track material and energy inputs and waste and pollution outputs, as well as services provided by the system over the entire life cycle. To do this, most people look to the ISO framework or guidelines. There are lots of different standards and guidelines out there for LCA, but this is by far the most cited. And we typically envision conducting an LCA in 3 steps. The first is goal definition and scope. And here the key steps include defining the system boundary of analysis. This essentially lets us decide what has to be included or excluded from the analysis. And you'll see as I continue with the webinar why this is such a difficult step, but also an important step. The next step is life cycle inventory assessment. This is really the accounting step where we actually track all those material and energy inputs and waste and pollution outputs from the system. And when we do this, I always like to emphasize that we're looking at a system or maybe a product or a technology, and of course we'll talk about more complex ones, but let's think about just a product or technology. We're looking at primary materials, secondary materials, energy going into a system, and then basically pollution and waste coming out of the system. When we do this, we actually think about the entire supply chain for the inputs to the system and even for the final disposition of waste flows. So as an example, every construction site, let's say we're constructing infrastructure, requires diesel fuel. When we model the diesel fuel, we don't just think about consuming it and emitting combustion-related emissions. We actually think about the entire fuel cycle or the entire life cycle of the diesel fuel itself. So one conceptual model to think about is like a branching tree where each input to the system is really a branch and additional branches come off of it, right? Because we're looking up the supply chain for every input to the system. The last step is impact assessment. And this is where we translate this inventory that we've created of environmental flows into something meaningful in terms of environmental or health indicators. And you can imagine the life cycle inventory is an enormous spreadsheet, and unless we can translate it into something that we can interpret, it's hard to really learn from it. So here's an example of life cycle impact assessment. I have just a few potential life cycle inventory flows shown in blue, and then I'm linking them to impact categories where we'd have indicators that would translate these flows into something we can understand better. This is also an opportunity for me to highlight what makes LCA different than other environmental assessments, and in particular, footprint. So a lot of folks have heard about carbon footprints, but haven't actually heard about life cycle analysis. Footprints tend to examine one impact category alone and often will include a life cycle perspective. So that's true for a carbon footprint. One of the goals of LCA is to actually make sure we're not trading off impacts, right? So let's say I come up with a technology that gives me great reductions in CO2 emissions, which are important for climate change, but has very high toxicity impacts. I don't want to understand trade-offs if I'm going to invest in this technology or put it out there. LCA can do that, while a footprint wouldn't be able to do that. And I should also point out that not all footprints are life cycle based. So the water footprinting method, for example, is not a life cycle basis in most cases. So there are other environmental assessment methods out there, of course, and I'm just going to highlight some of the differences between LCA and those methods. One example might be environmental impact reports, which usually focus on the impacts at the site of a project. And these analyses are sort of geographic in scope if you think about a site-based analysis. And they can include consequential effects, for example, induced truck traffic that might be caused by a new facility or building or something like that on a site. But they don't consider the whole supply chain. And of course, a product supply chain occurs over great distances in many cases. And so you don't have this geographic boundary when you do an LCA. In greenhouse gas accounting methods, we often are looking just at the site or economic sector level, or maybe a region. And again, we don't have a supply chain or life cycle perspective in many cases. And it would be incongruous if we did, because you would end up double counting. So I'm just trying to point out the differences, not not necessarily saying that LCA is actually better in every case. All right, so in transportation, I argue that we increasingly need a life cycle perspective if we're going to understand impacts. And I'm giving examples here of passenger vehicles and their fuels. So if we think about historically the impacts from vehicles and the fuels that they burn, the dominant source of impacts was the operation of the vehicle, which was really the combustion of fuels. So the production and disposal of a vehicle and the what happens before combustion, so the life cycle of producing a fuel, didn't matter very much. But if we look out to the future, for example, biofuels, if we ignore what happens before combustion, we've missed essentially nearly all the environmental impacts. And for future vehicles, we also can miss out a large portion of the impacts, both because the vehicles are more efficient, but also because we might be investing more upfront to gain that efficiency. Now, cars and fuels are not the only thing that are not all of transportation, but they were actually an early target of LCA. So a lot of vehicle-related LCAs showed that the use phase was extremely important. And then a focus on fuels, of course, emerges from there. And biofuels were, and I believe remain, the most studied product when it comes to LCA. And this is partly because transportation fuels and biofuels in particular are probably the most and first target of life cycle based policies that have been implemented, probably most notably the California's low carbon fuel standard. Non-car modes have also been studied with LCA, and these often focus on modal comparisons, meaning which mode is better environmentally than another. And also thanks in part to Professor Chester's really good work on this, they also reveal insights on the importance of operations and behavior, things like ridership, in determining the performance of different modes. In terms of infrastructure, pavements have actually been widely studied with LCA, and they really focus mostly on comparison of material selection. So what material you're going to build your pavements out of. And in fact, the Federal Highway Administration has LCA guidelines for pavements. I'm not sure how many federal agencies in the US have LCA guidelines. It might be one of the only ones. There have also been a number of European countries that have set requirements for either carbon footprints or LCA as part of roadway procurement or bid processes. So again, it's been a very ripe area for LCA. Other transport infrastructure has been evaluated as well, although I don't think quite as extensively. And again, they tend to look at comparisons across modes or some kind of payback time associated with investing in a new infrastructure. So I'm going to talk a little bit about biofuels because they are so frequently studied, and they've actually helped us, I would say, make LCA more sophisticated over time because they've identified some real challenges. So when LCA-based policy was first implemented for biofuels, a few things became evident. One, the challenge of standardizing LCA data and methods. And then the second, the importance of consequential as opposed to attributional LCA. And when we talk about consequential LCA, as I'll show you in a moment, understanding interconnections between the system we're studying and other systems becomes really important. I want to also take a pause and talk about some verbiage, okay? So consequential LCA is approximately the same as prospective LCA and change-oriented LCA. And attributional LCA is about the same as retrospective LCA and accounting type LCA. When you look at sort of a traditional LCA of a product, let's just think about a packaging decision like plastic or aluminum for a beverage. These are often going to be attributional LCAs. So these traditional LCAs where people made a choice about materials, for example, typically were attributional LCAs. So consequential LCAs are about changes to a system, and they're very policy relevant as we'll see. So in this example of looking at biofuels, if we break down the biofuel life cycle into three main steps, we have to grow a feedstock that gets used to produce the fuel, then we convert that feedstock to a fuel, and then we combust the fuel. And traditionally or historically, basically the scope of the LCA was really retained in this brown box I've drawn around the steps there. But once biofuel policies were implemented, it became clear that one thing had been missed, and that's the indirect land use change effects. So when we divert or grow feedstock to be used as feedstock for biofuel instead of food or feed, we send market signals around the world that say, hey, it's time to plant more grain or substitutable feed products because we're using this for ethanol now or for some other biofuel. So these are indirect land use change emissions. And in fact, if we think about consequential LCA, so that's a consequential problem. As a consequence of demanding more biofuels, we cause these indirect effects to occur. And this is why consequential LCA is important. So when we do consequential LCA, we have to think carefully about interconnections. So here, I just talked about a market-mediated effect, but we can also have other kinds of effects. So individual or collective behavior effects. This is really important in transportation. Think of things like induced demand, for example. And of course, government or policy actions can actually drive behavior changes and market changes as well. So it's important to think about all these potential effects when we talk about consequential LCA. And I've borrowed a figure that Professor Chester published in one of his papers in 2014, which is, I think, an elegant way of framing the problem of retrospective versus prospective or attributional versus consequential LCA. So what we have here is a technology-oriented assessment, which is basically a retrospective or attributional LCA, where we're directly comparing modes of travel. This was a paper on high-speed rail. So we can directly compare travel modes of car, air, and high-speed rail, and that's shown on the left here. If we think about this as a consequential LCA problem or a prospective problem, then we actually have to think differently about this. We have to think about the impacts of high-speed rail, but then also potentially avoided impacts by providing a new transportation mode. So we've changed the system. This is why we often call it a change-oriented LCA. And so in the case of high-speed rail, it's important to consider avoided impacts when passengers choose to move from car or air travel to high-speed rail. So I'm going to give an example from an infrastructure example on the importance of understanding interconnections and in consequential assessments, but also in terms of understanding interconnections to even represent an attributional assessment. And that's in a pavement LCA problem. So again, most pavement LCAs focused on material selection, design decisions, but the interaction between pavement and the traffic using it can actually dominate environmental impacts. For example, congestion effects caused by work zones can have lots of effects on air pollution and increased fuel consumption. But I'm going to talk about one that has more long-term effects, which is the effect of pavement condition on vehicle operation. So it turns out that the roughness of a road can affect the fuel economy of a vehicle, and roughness is a function of the pavement condition. So I picked a case study in Los Angeles, so a section of I-5 that was in need of some concrete slab repair. This is a high traffic road, so 80,000 vehicles per day, and about a quarter of those are trucks. And we have four options. We can do nothing, so we can continue in a disrepaired state, which means just pothole patching. Very smooth rehabilitation, a medium smooth rehabilitation, or a rough rehabilitation. Obviously, in the study, these are carefully defined. But what's notable here is that if we look at the options, what I'm showing you here is cumulative energy savings, okay? And construction, of course, consumes some energy in the form of materials and fuel, and so there's a small debit there. And then over time, we basically, because vehicles are operating more efficiently, we save a lot of energy. And the two red lines show us the best outcome, and that's because the pavement is repaired and made very smooth. The roughness goes way down. The difference between the two red lines is just a difference in assumptions about traffic growth over time. So the takeaway here is that if we ignore the interconnection between pavement and vehicles, we actually might be ignoring the largest impact that a pavement decision, a management decision, could have. So in this case, and in many cases, an LCA like this could actually be elaborated to assist in decision making. For example, in this case, a network-wide analysis of pavement condition and vehicle effects was done at a state level, and that could be used by Caltrans or whatever the state DOT is to prioritize rehabilitation decisions. So that's an example of turning an LCA into a decision-making tool. The other thing I want to point out is it's really important to probe interconnections. We cannot anticipate what is going to be important. We have to probe and figure it out. So we have to identify potential causal linkages between our system and other systems. So I'm going to give an example here of probing. In this case, we were concerned that improving the pavement condition would change vehicle behavior, meaning driver behavior, that they would drive faster, which is less fuel efficient. So we actually checked this out and made sure that in California, for roads being improved at around the level that these roads were being improved at, that actually we couldn't demonstrate demonstrable speed changes in vehicles. So we don't think that these interventions would actually change driver behavior. But it was important to probe this and validate our assumptions. All right. So with that, I'm gonna stop there, and I'm happy to hear some questions.
Okay, thank you, Alyssa. I failed to mention before the webinar that if you're joining us on YouTube Live, there is a chat window as part of that interface, typically on the right side if you have your YouTube Live in standard mode, not in full screen mode. And we're taking questions for this webinar via that chat interface. To give a little bit of time for those questions to queue up, I do have a few for you, Alyssa. So you mentioned the congestion effects caused by work zones. It's a temporary or transitional issue, but it does have life cycle effects. I was wondering how the magnitude of those emissions or those impacts might compare, those temporary impacts might compare with either the on-site construction-related emissions or the impacts, or the emissions or impacts for the life cycle impacts of that infrastructure.
Sure. So actually, the answer is that it depends a lot, and it depends first and foremost on traffic levels. So the same study I talked about at the network level, for example, if you're doing a rural road that doesn't have a lot of traffic, the materials are always going to, and construction event will dominate, whether it's work zone traffic or the effects on road users. So the most important parameter there is traffic level. And the second thing to point out is how the construction site is managed. For example, California really works hard and spends a lot of extra money to do nighttime construction to reduce that work zone congestion. So it tends to not be as large as, for example, the effect of the pavement condition on road users. So the answer is that it depends, and the most important factor is traffic flow, and the second most important factor is how work zones are managed.
Okay. Now, given that a lot of the rationale for expanding roadway infrastructure is to relieve traffic congestion, it's likely in a lot of cases that there are high traffic flows at the sites of these construction projects. So it's definitely something to be concerned about.
Yeah, and if I might add, I took this out of the presentation, but one of the key interconnections and consequential effects we need to think about is things like induced demand. So when we widen a roadway, we relieve congestion temporarily, but it tends to actually induce demand in the future. And so that can actually mean that in the long run, widening a road could actually, increase emissions impacts when we take a long view. So again, that would be a consequential issue that we'd have to model and understand.
Right, thank you. So I'm going to turn the presentation over to Assistant Professor Mikhail Chester now at Arizona State University. I'd like to remind those of you on YouTube Live that you can join us. You can ask questions via the live chat on the right side of the window, and we will be collecting those for the discussion portion of the webinar after Mike's presentation.
So thank you, Juan, and thank you all. I'm delighted to be following up on Alyssa's presentation. And what I'm going to try to do is talk about a few particular aspects of LCA, specifically uncertainty, the significance of ridership, and then what I'm going to do is go into decision making, where I'm going to try to talk about what matters in the context of transportation LCA, where should you be focused in the life cycle of transportation systems and why, and ultimately try to connect that to a short discussion on NEPA and CEQA, how LCA might fit in there. So before I get going, let me give you a little bit of context of who I am and why I'm speaking to you. I've been working in the area of transportation life cycle assessment for about 12, 13 years now. What started as graduate studies has become part of the sort of research program that I have here at ASU. When I started in the mid-2000s working in transportation LCA, the field was, still at its very beginnings. We had seen a handful of LCAs, and when I say a handful, I mean probably under 10, trying to think comprehensively about the life cycle impacts of transportation systems, including things like the components like the manufacturing of vehicles, infrastructure, and fuel chains, as Alyssa has talked about, energy supply. So I came along and I sort of surveyed what had been out there, and one of the key missing pieces was sort of a critical look at infrastructure. And one of the reasons for that is because infrastructure is so diverse across geography, across the transportation system, across the modes and so on. A light rail system in one part of the country in one city looks very different infrastructurally than a light rail system somewhere else. So I have dedicated a considerable amount of time to trying to understand how we characterize the life cycle impacts of infrastructure within the context of transportation and why it matters. And that has led me to not only questions of how you characterize the environmental impacts, as Alyssa started talking about, of these processes and components, but also how did the design of these infrastructure affect ridership or affect the use of transportation systems? How do we see mode shifts depending on how we deploy transit in more or less accessible ways, for example? So picking up on the background that Alyssa has given, the very nice background that sort of characterizes the stages of LCA and sort of where we are, I'm going to talk a little bit about uncertainty. And instead of talking about uncertainty in the traditional sense of showing you guys a bar chart that has a little line that is an error bar that is usually totally useless because you don't know what to do with that little error bar. I'm going to try to characterize uncertainty and how we think about it across LCA, and then talk about the ways in which we deal with it. So I've thrown up here a handful of categories in which we might think about uncertainty within life cycle assessment. So when LCA began in the United States, it was roughly the early 90s. You know, we were just sort of learning how to do it. We didn't have pretty much any data on you know, the environmental impacts or the materials or the process requirements associated with, you know, virtually any of the processes associated with the systems that we're interested in this case, transportation. So by the early mid-2000s, you know, you had seen a number of LCAs that had been done. People had started collecting data. The digital age was upon us, and, you know, data was becoming more available. So you know, that led to the ability to do more quantitative uncertainty assessments. You know, now 10 years later, we're sort of in this future of, you know, large data sets. And while I would love to say that large data sets exist for, you know, everything we would like to consider in LCA, the reality is that, you know, often we're lucky to find large comprehensive data sets for the things that we're evaluating. But when we think about uncertainty within LCA, you know, often we're thinking about, you know, for example, the geographic space. You know, are we collecting data that are from the, for example, transportation system that we are evaluating? So if I'm evaluating a system in Los Angeles or in Phoenix, am I collecting data, or do I have data that I've gotten from some website or a publication, or maybe somebody else's study that is specific to that location? And if I don't, well, how does that matter? How would the data change if I were looking at, for example, energy consumption of a light rail train in Phoenix versus Boston? Similarly, temporally, you know, data, our technologies change over time, and as such, the data that we're collecting should reflect that. So, you know, cars, for example, have become more fuel efficient over time, and if we're, you know, evaluating a vehicle today with data from 10 years ago, there might be a problem. The sufficiency of the sample size is another big issue. So often in LCA, we are dealing with lots of processes and sub-processes. So for example, in my transportation life cycle assessment models, for a particular mode, say an automobile or light rail or air travel, there might be 200-300 life cycle processes that I'm modeling, from you know, the herbicide use on the rail track to salt on a roadway to, you know, the energy requirements of the vehicle itself. And, you know, sometimes we have very few data points to use, and at other times we have large, rich data sets. And one of the things that I would like to impress upon the audience is to start thinking about data collection, not purely from a, you know, typing in a search into Google or searching for a particular publication, but collecting data on your own. So this is an area that I think leads to you know, significant and fruitful insights into what's happening with the specific technologies that we're interested in. Going on, a couple others: independence of data supplier. You know, are we getting information from a source that is unbiased? Or are we getting information from a particular industry, let's say, that has a vested interest in a particular technology? And then lastly, technological correlation. One of the things that we deal with often in LCA is that we have data for a particular process, say, you know, putting asphalt down in the construction of a roadway, but the technology may not quite match the particular technology that's going on in our study area. So there's lots of variables where we think about uncertainty. One of the first ways that we start to think about uncertainty, managing all of these different processes and the complexity that is the life cycle boundary, system boundary that we're evaluating, is by doing what's called a data quality assessment. It's a qualitative approach where we essentially look for the places in our study where we might have problems with some or more of the variables or characteristics that I'm mentioning here. when we do the data quality assessment, we tend to look at, which of the variables are leading to more or less uncertainty in our analysis, which gives us a sense of where we should focus our efforts as we try to improve the quality of the analysis going forward. Ridership tends to be a critically important variable in transportation life cycle assessment. The listeners, the audience may be saying, duh, of course it is, but I want to unpack and focus critically on why ridership tends to be really important. So, yes, ridership is important from the stance of, evaluating the impact of the mode if you have, one person riding a car versus two. But I also want to sort of merge that discussion with what Alyssa mentioned earlier in the sort of framing differences of LCA in the attributional versus consequential perspective. So what you see on my screen here is on the left-hand side, what Alyssa characterized, I would say primarily as an attributional life cycle assessment. So this is some hypothetical emissions per passenger mile traveled. It could be CO2 emissions, it could be NOx emissions, it could be particulate matter emissions, it could be energy use per passenger mile travel. It could even be dollars per passenger mile travel. We could think about LCA impacts fairly broadly here. And what I've done is I've shown 4 bars, an automobile with 1 passenger, an automobile with 2, then a bus with 10 passengers, and a bus with 40 passengers. So, you can think of a bus with 40 passengers as being peak, a bus with 10 as being off-peak. I think the average in the US about 10 years ago was about 8.5 passengers on a bus at any given time. But, we want to think about off-peak versus peak, right? So peak might be 40. And off-peak might be 5. But what this chart is doing is giving you a sense, and then, sorry, the life cycle would be the gray being vehicle operation, that's the so-called tailpipe emissions, the blue being the manufacturing and maintenance of the vehicle, and the orange being the infrastructure itself. What you see here is that the emissions per passenger mile traveled go down when you have more passengers. Specifically, they go down by a factor of 2 when there's 2 passengers on a car versus 1. They go down by a factor of 4 when there's 40 passengers on a bus versus 10. This may seem obvious. I don't know if it is. But when I originally started this work in 2009, or originally published this work in 2009, I got considerable press attention because it was one of the first times that somebody had kind of quantitatively shown this, particularly within the context of LCA, and the significance became apparent of the difference between low and high ridership vehicles. On the right side, you see the so-called consequential framing. So, what I've tried to do here, and again, these are all hypothetical results, please don't use the data or go cite them. Well, what I've shown here is the same vehicle manufacturing operation and infrastructure over time from 2020 to 2017 as the result of, let's say, the decision to implement new transit, which adds emissions. So let's say I add a new bus line in a city. Well, if it's burning compressed natural gas, or diesel fuel, it's going to be emitting, let's say, CO2 emissions, but hopefully it was designed in such a way that it's attracting riders away from, let's say, an automobile onto that new bus line. So you're going to have avoided automobile emissions. So that would be the below zero emissions. And the idea here is that we can look at the net effects over time and say, well, we're adding emissions, but we're subtracting an even greater amount. And the net result is hopefully a savings by some point in the future. Well, the savings at some point in the future are driven by that ridership shift, right? So if I have a large number of people that are shifting to transit that would have been taking the automobile, well, then I'm going to have a lot of avoided automobile emissions and relatively fewer transit emissions. And an example I'd like to give, Alyssa gave a number of examples on attributional versus consequential, but when about 5-6 years ago, I was working on a project in Los Angeles on the life cycle impacts of a number of the new transit lines. And we were focused in this context specifically on the orange bus rapid transit line. It's a compressed natural gas line that runs through the San Fernando Valley. And the bus had begun operations, and there were some preliminary ridership surveys that had been conducted that seemed to indicate that most of the passengers had been shifting from the slower local bus lines to the new rapid bus line. And when you carry that through in terms of, why ridership is important, well, here you had a scenario where if you followed up and you asked LA Metro, well, what did you do with the existing local bus lines? Well, they were still in operation. So effectively what you had done is added a new bus rapid transit line with CO2 emissions that didn't exist before, and you had not removed any existing transit service, so those emissions were still happening. So the net effect, the change of emissions for, say, the regional inventory would have been positive. Luckily, a follow-up survey that was done a couple years later showed that a significant number of riders in the medium term, now we're probably in the long term, had been shifting from the automobile, so you would get more of the effect of what you see on the right here. Ridership and uncertainty, we can think about those two together because they're so critically important to driving the results. So here I have a snapshot of a study that I did on California high-speed rail. And what you're seeing is the potential greenhouse gas emissions for passenger kilometer traveled when you have a large number of passengers on the mode. So for example, for a car, 5 passengers would result in roughly 80 or so grams of CO2 per passenger kilometers travel versus 1 passenger, which would result in roughly 380 grams of CO2 per passenger kilometer traveled. And one of the ways that that I would advocate thinking about the significance of ridership and when we have one mode emitting more or less than another is what I've called a break-even analysis. So here you can see that at a single occupancy automobile, you need roughly 270 people on California high-speed rail, 59 people on heavy rail, which is essentially Amtrak, and 37 people on an aircraft in the long-distance trip that is San Francisco to Los Angeles to break even with a single occupancy automobile. So this gives you a sense of one of the ways in which you might frame it. It leads to lots of other discussion, which I'm happy to take questions on. So for example, what is the average ridership expected to be, and what does that mean? But this gives you one way in which you can start to say, given all of the uncertainty, particularly in this case around ridership, how do I frame it in a way that's palatable, in a way that's consumable? Another way that I've tried to do this is by showing what you need to do in terms of ridership to get a payback and how fast that payback would be if, for example, you're implementing a new transit line or a new mode in general, we can say. So this chart is showing that at a certain percentage of trip takers, in this case for the orange line in Los Angeles bus rapid transit again, not to pick on that one, but we've done a lot of thinking on that line. When is the payback in terms of avoided automobile trip takers? So for example, at around, we'll focus on greenhouse gas emissions, which are the sort of maroonish color. So at around 25% of passengers having bus rapid transit passengers having shifted from the automobile, you would start to get a payback. However, over the long term, if you've got more than 25%, then that payback would happen faster and faster and faster. So this gives you a sense of how that payback occurs, but it also shows you that payback occurs differently for different pollutants. So it's not always the same because those pollutants occur in different ways across the life cycle, as Alyssa has already pointed out. I'm going to try to finish up in about 5 minutes here to make sure that we have sufficient time for Q&A. Shifting to decision-making in LCA, there's a lot of ways that we could have a conversation about decision-making if time allowed. But one of the things that I would like to sort of boil down all of the different processes and parameters associated with the life cycle that both Alyssa and myself have talked about are, these 6 variables, so to speak, that really matter a lot in transportation LCA. So not to say that other things don't matter, depending on the question that you're asking, depending on the system that you're evaluating, they very well may. But there tends to be, I've done probably 100 transportation LCAs at this point, and there tends to be these 6 variables that kind of rise to the surface as being, the things that we really want to think about in the context of engineering and planning decisions on LCA outcomes. So one is, shifting energy burdens. when you're doing a transportation LCA for decision making, or whether you're thinking about how to make decisions for transportation LCA, energy burdens and where they occur tend to be really, really important. So, yes, the tailpipe of vehicles, so to speak, if we're looking at electric vehicles, power generation, or transit vehicles, power generation, we can go to those scope 2 emissions. So shifting of energy burdens tends to be a big one. You need to look across the life cycle of where energy is happening. Yes, both with propulsion of the vehicles, but also in other places it tends to be significant. The infrastructure tends to be significant, and actually it tends to be more significant for transit modes than for automobile modes. And why that is because the amount of stuff, physical material that we put down for transit tends to be a lot greater for the passenger miles travel that it facilitates than for an automobile. That doesn't mean necessarily that the life cycle impacts of transit are higher for transit than a car, but they tend to be relatively higher within the respective life cycle, meaning for an automobile, the infrastructure might account for 20% of life cycle impacts. For transit, it might account for 30, 40, 50%, again, depending on the system you're looking at. Operations, absolutely. So engineering planning decisions that affect operations are going to affect the LCA outcomes, as I've already pointed out, possibly through ridership, possibly through the need for new vehicles. And then supply chains. This is one that's kind of not usually apparent to people, but the decisions that are made within a particular context that affect supply chains tends to be very, very significant. So supply chains, manufacturing a car in Detroit, a transit vehicle somewhere, and then bringing it to a particular city. Those supply chain effects, the energy mixes that are happening under, for example, tend to be significant. And lastly, the interdependency of systems. I'll come to this in a second when I talk about NEPA and CEQA, but the interdependency of infrastructure is one of the core, or of systems in general, is one of the core aspects that LCA shines light on. The other is complexity, the other being supply chains. But we have to fundamentally recognize here that LCA gives us perspective on how our system that we might have control over is intimately interconnected with other systems that we may not have control over. And that raises very interesting questions about how we reduce, for example, environmental impacts in upstream supply chains or in interconnected systems that we may not be able to have control over. Let me just spend 1 or 2 minutes on NEPA and CEQA because I know that is the sort of hammer of environmental assessment and getting things done. I will readily admit that I am not a NEPA CEQA expert, but just scratching the surface here, I wanted to give a few insights in terms of how LCA might be valuable in the NEPA or CEQA or environmental impact assessment process. So, LCA can clearly support this set of questions of where or will there be significant impacts. It gives us a standard framework that Alyssa clearly identified of how we should think about a transportation system, where we should look for impacts, and then ultimately where the hotspots might occur, and that leads to what we should be doing about it. There are some early studies that have laid out frameworks, more kind of decision tree type thinking on how you can decide whether or not to implement an LCA to inform environmental impact assessment or statement. So this flow chart, I'm guessing the slides will be made available online, and there's a study here that you can search for in the top right that gives a walkthrough of how to use it. But there have been attempts to basically identify would LCA actually provide value for the environmental impact assessment, and if possibly yes, how much so that ultimately might lead to some insight into whether or not a full LCA should be implemented to help support that EIS process. There are certainly overlaps between LCA goals and NEPA CEQA goals, but I would not say that those overlaps are 100%. So, yes, LCA and NEPA CEQA try to get at both direct, indirect, maybe even some supply chain processes. Ultimately, though, I would argue that LCA is primarily focused on questions around system interdependencies, complexity, and multi-jurisdictionality of impacts, which, those goals could be aligned with NEPA CEQA, but they are not always are, right? So, there's certainly a subset of goals within LCA that could be of value in the NEPA CEQA process, but I would say there's another set of goals within LCA that aren't necessarily. So I don't necessarily advocate that LCA become a necessary requirement in NEPA CEQA, but there are certainly times when it could be of value. One of those times, for example, is the strategic assessment process, where both Alyssa and I have pointed out how larger decisions that affect a transportation system could be evaluated with, for example, consequential life cycle assessment. With that, I'll end, and I'm guessing that Juan is going to open it up for questions. So thank you all again. Last thing I'd like to point out is that I try to compile LCA studies and data for everyone on this website, transportationlca.org. So you may find that resource useful.
Thank you, Mike. Okay, anybody joining on the YouTube webinar, we have a chat window available if you would like to ask questions during this about 13-minute question and answer period. I have one for Mike to kick us off. So given that ridership and mode shift have quite a significant impact on LCA results, most people, when they think about project planning, they think about decisions made before the project, about design that lock in certain infrastructure, having the overall impact on whether or not a project might produce benefits, and over what those magnitude of those benefits might be, and over what time frame those might occur. Given that ridership is so important, there could be potential for those soft decisions, softer programs that an agency has, like a marketing program, like first last mile investments and safety programs that actually have an impact on programs that influence behavior, might have an impact that occur 10, 15 years down the line, might have an impact on a project's life cycle results over many decades. Now, I suspect the effects are difficult to measure, but what might you suggest for somebody who's thinking about the LCA of a marketing program or a minimal infrastructure program?
Yeah, so great question. I pulled back up this sort of payback slide. So you hit on a couple of things, these sort of hard versus soft options. We might characterize them a little bit differently depending on the conversation. But first thing to think about is infrastructurally, there are things that we do, like build a track that goes through a city, for example, with concrete infrastructure, steel infrastructure, and so on. And then we have transit overlay districts, for example, that we might incentivize certain types of land development to encourage ridership. So there's a subset of strategies that we need to think about early that guarantee us that we're going to get this environmental payback, that it's going to happen. Again, environmental is not the only dimension that we think about with transit, right? There's many other considerations, but in the context of environmental LCA, we do want to be thinking about those early decisions that essentially lock us in. That basically say, this is going to mean that we have only so much that we can do in terms of infrastructure in the future, because we've locked us into this particular infrastructure design that's ultimately going to affect ridership. In the long term, what I would advocate for is thinking critically about these strategies that you mentioned, Juan, the softer strategies that might affect ridership in what I would characterize as a dynamic LCA, or it takes on many different names, evolvative LCA, depending on what you're reading. But there's, I would advocate that we're thinking continuously about where environmental impacts are occurring and what could be done to eliminate them. And those, those might be strictly focused on ridership. Those might be more broadly on things like, energy mixes.
Okay, thanks, Mike. Alyssa, I'd like to invite you to rejoin on the screen. Okay. And so now I have an additional question for the two of you. And I guess it kind of relates to the California experience and practice. So there was a Supreme Court case in California in 2014, Center for Biological Diversity versus Department of Fish and Wildlife. I'm not going to ask about that case, but what it did is it specified how local agencies would handle significance of greenhouse gas impacts in EIRs. And essentially they're looking for consistency with state level and regional targets. Now, I have a question about those state level and regional targets. I know that Alyssa, that you've done work on global warming potentials and the timing of impacts of climate change impacts from different types of global warming pollutants. And Mike, you've done work on the cumulative impacts or the cumulative emissions over time based on the timings of when reductions might occur. So policymakers often express goals as percentage reductions in CO2 equivalent, so normalizing all greenhouse gas emissions by some future year. And I'd say from an academic perspective, there's a lot of there's a large range of climate impacts that might occur while meeting that target. So given if you're releasing a ton of methane in early years, not a ton, but a large amount of methane in early years, and you're using global warming, 100-year global warming potentials, you'll have a larger impact. So I just wanted you to discuss the way that policymakers tend to set targets versus the actual climate impacts.
Alyssa, do you want to go first?
Well, I guess I'll have a two-part answer. One is the challenge of policy is that it has to be simple enough to implement. And I'm an enormous proponent for understanding the consequences of emitting greenhouse gases, like the real consequences, which means we should care when they happen. On the other hand, not every sort of mitigation target or goal actually will sort of have a time component that's very important. And so, for example, there are certain systems where you have a really high upfront investment and you get your benefits over a long period of time in the future. And those are the ones where you probably need to consider whether or not the timing of emissions is important. My inspiration for actually working on this topic was that the EPA applied economic discount factors to land use change emissions for biofuels. And I thought, I'm pretty sure we have a physical basis for understanding the importance of when an emission occurs. We don't need to do economic discounting because economic discounting is, it's a mathematical form that doesn't really make sense in the context of how greenhouse gases behave. So, so my first answer is, I don't think, I mean, policymakers have to balance complexity of a policy or regulation with their goals or what they want to achieve in the long run. And that may mean simplifying the equation. The other side of the coin here is that, for example, the ARB now has focused on reducing the short-lived climate-forcing pollutants. And that's because sort of in support of understanding the importance of time and irreversibility, and they're focusing on getting near-term reductions that could be large. So focusing on reducing those methane emissions and other high GWP gases that are shorter lived. So that's sort of a policy solution in a way to a time issue that doesn't actually require a very complicated regulation. So if a regulation implements my method, I've already proposed that, apparently not going anywhere. But part of the problem is the complexity, right? So I do think the policymakers have this challenge of trying to achieve a real outcome, but also understanding that the way that they set up the policy has to be pretty straightforward.
And I would add to that with the idea that, LCA, particularly consequential LCA, puts us in, or gives us additional insight that is often not considered in terms of, setting these targets and meeting these goals. Specifically, how quick we need to be doing things in order to meet those goals, right? So Alyssa commented on the relative impact of certain emissions. The other side of it is, how quickly we need to be doing stuff. So, for example, if we are saying everybody or a lot of people need to be taking transit to meet these greenhouse gas goals, well, that means we're going to have to put all these land use policies in place coupled with new transit lines or improved transit service so that we get people out of cars. And the goal is that by 2040 or 2050, we're at some greenhouse gas reduction level. Well, though that implementation needs to happen at a fast enough pace to actually meet that goal. And LCA actually gives us a framework to understand the pace that those changes, those infrastructure or policy changes need to happen at to be able to get there on time.
Okay, I have one last question before we wrap up. We're approaching the hour. For those on the line who work at transit agencies or work in environmental assessment, what are the greatest data needs for making transportation LCA more robust and more complete? So being able to conduct assessments for more areas of the country on more different types of projects.
I'm not sure which one of us wants to go first here. I haven't done as much work on transit as Mike has, but my experience so far is that there's sort of there's not consistency across the kinds of data that are publicly available and unavailable. And I also my experience looking at infrastructure is focused on construction of roadways and rail, and in both cases we had to depend on commercial databases to understand the impacts of particular materials. Those commercial databases are proprietary, so it's hard for us to provide sort of open source underlying information. And so I know that there's an effort right now in some of the pavement community to come up with environmental product declarations for different key materials. An environmental product declaration is a consumer-facing like summary of a life cycle impacts around a material that are guided by product category rules that are agreed upon by industry or stakeholders. And in theory, these are approved or managed by third parties to make sure they're more objective. That's an effort to actually make data available publicly that is verified in some way and not protected under a database license fee.
Yeah, I have spent many days in transit offices siphoning through often decades-old paper and, if I'm lucky, newer data in digital form. And what I'm generally looking for is a few key data sets. And this is in the context of executing the LCA. The first is information on the infrastructure. And we often will find that in design documents. And very few people save design documents or make them publicly available. So, cross sections of roads and tracks, overviews of how much material is used is a data set that I have almost never found, but is critically important. What materials were used and why, how much did they cost, how extensively were they used? Because with that information, I could probably provide insight into ways to reduce the environmental impact of certain material uses. The other side of it is the non-infrastructure side. The operation side would be operational characteristics. This still, for some reason, is a very difficult data set to get your hands on. There's a few transit agencies that tend to summarize the data and put it online, but providing line by line data at peak versus off-peak, daily, weekly timescale is critically important to understand, how decisions that affect transit or put new transit into operation are actually playing out. So those would be the two big ones that I would recommend.
All right. Well, thank you. So I'd like to thank Alyssa and Mike for joining us today. Those of you on the webinar, you can find, I invite you to subscribe to our YouTube channel, where you'll find another 22 videos, webinars, live talks from past events that UCLA ITS has had. The video link for this webinar will be available immediately after the broadcast. So if you'd like to share it with your colleagues, with people you know working in the field, feel free to do so. So thanks again, Mike and Alyssa.
Thank you.
Thank you.